Today's talk is on processing visual scenes. So our speaker is Associate Vice Provost for Research at UAA. He received his both his master's and PhD in mathematics. His master's was from University of Pennsylvania.
Yeah.
And he was a director of the Visual Processing Lab at Stevens Institute, where he was his last academic post before he joined UAA. So, just to give a little lead to the research area, processing visual scenes is extremely difficult. What we humans, what a 2-year-old can do without problems is extremely difficult for machines to do. Just recognizing the difference between foreground and background is still really hard and open question. So segmenting or cutting out what object is in foreground versus what else is in the background is difficult. Getting semantic understanding of what is happening, or if the semantics of what is happening changes from image to image, is even harder. And when we look at, and this is all in images, when we look at processing video, that adds yet another layer of difficulty and complexity. So this research area kind of spans many fields from robotics, cognition, psychology, computer science, and that's the expertise here. Are we ready?
So yeah,
Take it away.
so sorry for being late. I was waiting for our task manager from DHS to call, and he's a day and a half an hour late. But it's $17 million, so we'll wait. I'm really glad to be here, so the talk is about unsupervised detection of video subscenes, and it sounds like sort of very techy. Why subscenes, why not scenes? We'll see in a moment. I'll start with the motivation. I'm a mathematician by training, but I've done computer science for a long time, and every time somebody tells me I have a theorem to solve your problem, I say, let your theorem meet my data, see what happens. So this is actually a project that was funded by 3 National Science Foundation Awards, a Google Research Grant, and a Intelligence Support Office grant from DoD for about, it's actually a very old project, it's about 5 years and it's ongoing. The project actually is human terrain extraction from images and videos. So the story is a very typical story. We actually got initially about 750 gigabytes disk that came from somewhere from the field, and the question that the agency had is, tell us who is on this disk, what are they doing, and where are they doing it, and to whom are they doing it. And there is no annotation, nothing. So since they started, so now it's a continuously increasing set of data as more and more disks arrive from all over the world. What's very characteristic about this is it's completely unstructured. We just know this is videos and images that somebody captured for some reason. So presently it's about 7 terabytes of data, and it's growing. And basically what you're seeing here is part of the cloud service we are maintaining for the government, which eventually will move here. The goal is to find all the people you can recognize and establish the connections between them, build a social network from that. Currently we are in this 7 terabytes of data. We are actually monitoring about 1,300, this number might have changed, of individuals. We actually monitored many more, but it's an interactive system, so the analysts actually decided some people are not of interest and they removed from the network. But that's roughly what you see is a typical, so there are several networks. Actually, the project is a system of systems project. There is a network of individuals, there is also a network of places. Actually, it's a hierarchical data structure of places. And then there is a data structure that represents different activities. But let's concentrate on the individuals. So each node in the network of individuals is of course a person, and edges between nodes are essentially saying, well, these people were in communication at some point. They were interacting together. And so from this data set, how do you establish this? Well, if they were present in the same document, if you have evidence supporting them. So each edge has attributes which are the evidence that support the connection between the individuals. Another attribute, so the node attributes on the other hand are the participation level, because at the end of the day, not only we want to find who is doing what to whom, but there's a natural desire to figure out what is the communal structure. So how important are different people in this network, and center communities around the leads. So the data that actually is used to actually do the communal structure analysis of the network is the participation level of each in each document, and in fact there is a little bit more weight which comes from basically the number of edges that end in this individual. Based on this, you can do some standard community analysis, and you can break the network into communities, so you can actually sort of see a structure. Since it's a very large network, the analysts first see the different communities, and they get to choose community, and then they can get into a community and look at specific individuals. So, I mean, this in itself, basically maintaining this network and updating it, and actually working with these multiple networks is a topic of its own. But I want to concentrate here on something very small, which is how do we measure participation level? And the participation level, actually in static images, is really hard to measure, but at least in videos, you can sort of say, who's more active and what kind of actions they're doing. There's another point that's actually very important. At the end of the day, these videos, these are not stream of consciousness videos. They're not surveillance videos. They're videos taken by a person observing a scene. He's actually giving you cues who is important. Who's important to him, but he's giving you cues. And that's what you want to exploit. It's, from the computer vision point of view, this is a very strange set. We have had these data sets forever because we both use people used to buy cameras from Radio Shack and take them in the field and take videos. But some of them are JUTAC, some of them are, nobody ever says the date and time on his camera, so you basically have the date and time when the camera was produced. So that was a useless stack. But it's a very interesting set of data because it's ubiquitous. But it's really hard to work with because of the way you take these videos. So we'll come back to that. But the important thing is here is this is ad hoc videos of events. People really are shooting something that they care about, and often they shoot that, usually there's a lot of ground videos. Somebody's holding their camera. But when you actually can recognize people, that's actually meaningful. So this is actually an important thing. Based on the implicit cues that the operator is providing, we actually try to establish the relative importance of a person in a video. And then the next thing we want to do is, at the end of the day, we want to measure actually interaction between individuals. So this is essentially different units of action and interactions are what the videographer calls events, right? This is a scene. So we want to actually extract, for each video, we want to summarize the video with who are the core participants based on their participation level and the list of events that the video is describing. So I know my okay, now it's working. Let me see if this link will work. So I noticed that the mouse on my computer is not working. So that's why I'm using the touch screen. Actually, just fine. It's easy. So let me show you one typical video that actually came from the field. So this is the video, and actually the bottom of the video is the output of our system, but it's more important what's on the top. We have crowdsourced this. We have asked multiple experts to actually look at the videos, or actually we went to Amazon Turk, so we actually had several communities. We asked experts, but we also asked random people to basically look at these videos. This is the quality of the video, it's a pretty lousy video. And tell us, where do they put a mark? Where do they think that there is an event boundary? Where is there a break in the action? And it's actually here, what you're seeing here is this, because there are many people inputting, this is the probability of having an event boundary in some particular frame. What you're actually already seeing is that even though this looks like a simple video, people are breaking it. They sort of do this mental break into different pieces. They are actually sub-scenes, they're not full scenes. But on the other hand, they're somewhat uncertain, right? And the other thing that you see is that there is some hierarchical level. So a lot of people have strong response at these time points, but there are also some responses here, but they're with lower probability. And what this is really a representation of is the fact that actually we humans always do event segmentation in our stream of consciousness, but we do it hierarchically. We actually don't just do one event sequence event. We don't just do one event segmentation. We do many levels, and it's actually done subconsciously. It's precognitive process. So the unfortunate thing with this is that for a very long time, both the cognitive psychology community and the computer vision community has been used to establish firm event time boundaries. The reason why this is unfortunate is actually makes it very hard to evaluate algorithms. It's a the process of establishing boundaries, as you can see, is quite fuzzy. And having this really exactly established time boundaries doesn't make no sense. Yeah. Okay.
I don't see any events in there. What kind of events are we supposed to?
So I can tell. So let me see. So what? It's not really an event. It's actually the person is being surprised. That's where an event boundary is. What's really happening here is let's just see if I can slow this video down. Now that I don't have a mouse. So there was actually an establishing shot, and what here the person, so for example here you can notice, let's just see how I can bring this, pause this. Let's see if I can switch a mouse on. So in the annotation, what people are also annotating is, who do they think right now carries the action in the video. So the changes are really because some people are coming in and out of frame. That's what they are responding to.
So, can I ask you?
Yes. Yes, go ahead.
In kind of cognitive psychology as well as philosophy, we typically talk about all these things in terms of proposition. Like event being idea, where some specified subject being in the state of something or doing something. So the event can be some idea units that most people can either say it's true or false in terms of whether you can specify a particular subject or the particular actions or state.
So,
Is that
so yeah, so what here is again on this level is the change of state is the participants that the camera seems to be focusing on
That's right.
at different moments. And this is exactly what we care about, because we care about who this observer was actually observing, who was he centering on.
So in that sense, what you're interested in is not, well, there is an argument in philosophy as well as in psychology whether or not event boundary actually exists in the nature.
Yeah.
What you're basically implying is basically the perceiver or the video taker is actually providing the cue with respect to how he segmented.
So he's doing the segmentation.
Yeah,
now
that's right.
our problem is we don't have his annotation. We actually have the annotation of observers, which we have instructed telling them, look, this person probably cared about the scene. But to answer your question, these are not events in the way you understand an event. You understand an event as a football match. This is an event on a very low resolution level. This is on a very high resolution level. Me moving my lips and stopping to move my lips is already an event.
Okay.
So, yeah.
Maybe jumping ahead, but is this whole thing that you're starting to talk about been, like, say, tested with theater performances, where somebody would, like, say, film from here, and then the next performance, which is almost exactly the same, as
So it hasn't, because for a different reason.
You know, I mean, you've got your constant as the performance.
The reason why, so there is this thing that I keep saying, something about Hollywood style videos. Theater performance and Hollywood style videos and commercial videos and newscasts actually follow very well established grammar. Their events are punctuated by shot transitions.
Yeah.
And that's precisely what we are missing here. Here you have a person running in the field with a camera that's actually trying to capture something they care about. He doesn't have time to do shot transitions. He probably doesn't even know what the shot transition is. I mean, it's me, you, somebody bought a camera and was sending in the field and taking images. So that is the big difference. That's why. So here's my definition of an event. That's I guess it's Sachs' definition, Sachs and Tversky's definition, but it's pretty standard. It's a segment of time at a given location conceived by an observer to have a beginning and an end. Something started and something ended. That's where event boundaries are. And again, if we actually had theater, if we had drama recordings or Hollywood style videos or any commercial video, event segmentation is a pretty standard thing then, because you have these clearly established boundaries by the way shots are taken, and then an event is basically a union of these video shots. Here we don't have that. What we are actually trying to, at the end of the day, however incompetent or pressed an operator is, he most probably is trying to establish his own grammar. And that's actually another part of the project. The other part of the project is to try to actually classify the different operators that we have. Based on technique, but actually there is a much easier way. All cameras, all digital files have markers. We can actually establish what type of camera was used, when was the camera made, we know what the unit is. So, unfortunately, one unit can match many people, but that's a separate issue. So here, in a sense, in order to be able to evaluate, we have taken these input from different viewers, and we've created these firm time-shot boundaries. And what we want to really have is an algorithm that maybe, because these time-shot, these shot boundaries are some level of resolution in event recognition, and there is a continuum of those. We're trying to find an algorithm that works at a level of resolution which is higher or equal than this well established. These are macro events. So the fortunate thing is that most of these video we can go and use for papers because of control over the data. So we actually, a lot of the videos that I'll show is I had to send my students to go on YouTube and download videos that approximate the qualities of the videos that we're looking at that are for, public consumption. So people can actually run their algorithms on our data. So most of the stuff you will see is actually sort of pretty standard. Let me just play one more video. No, this one is very good. This is David Blaine doing the car trick. So the reason why I want to show you this video is, again, well, there are fewer events, that people could mark, and it's sort of a very interesting event because this is actually a very interesting thing because very few people actually consider a kiss to be an event. And I don't know whether this was cultural. We actually tried, when we selected our markers, we told them, well, anything you consider interesting, mark it as an event. And it was just a bunch of guys that actually marked it, all Europeans. So I don't know what does this tell you about human perception, but the truth of the matter is also some people did mark it. You could argue, well, maybe at different levels of resolution, because it's too short of an event. It's still just these two people communicating, so it's not really the characters have changed, but it's sort of an interesting phenomenon. Yeah.
Also, the one possibility which is going to make this more complicated is the person who's actually taking the video obviously has a view outside the screen. And that maybe influences basically what's going to be in the frame. So maybe basically the event structure that you need to extract from the person's, basically the viewer's mental representation is not completely based on the image in the scene, but something outside, obvious, because they shift.
Yeah.
That means he's also looking at something else as well.
So that's a very interesting point, which actually we'll come back to. We are making some assumptions about these people who are capturing the video. That they're purposeful, they're trying to capture an event, that they're stressed for time, which they always are, and that's actually one reason why all of these videos are very short. It's easier, so yes, you're taking the video and somehow you're losing your focus. It's easier actually to cut the video and start shooting again than actually adjust. So that actually will come down in our algorithms. This is actually an assumption you make for our algorithm. That they're purposeful and efficient in some ways. So anyway, so what we're really trying to do is we're trying to do again video segmentation the way people do video segmentation. We're trying to come up with shots so we can lump at very low resolution shots, or at least mid-level resolution shots, so we can actually, high resolution, very small shots, so we can actually start building this hierarchy of bigger and bigger events from them. Just kill this for a moment. So again, I'm a mathematician, but I do talk a lot with psychologists. Part of it is that we're using so much human input that we actually would like to mimic what people are doing when they do event segmentation. So humans do detect events all the time on many scales. There is passive automatic event detection. So this is the brain response where people are just watching the video. They're not even told to segment it. They're just watching it. And somebody has actually marked events at two different scales. And there is always, so this is an event boundary. And you can see where the event boundary always sort of coincides with an increase in activity. Often actually this increase in activity is a little bit delayed. This actually happens, the delay, the peaks usually happen much after the perceived the event boundary. This is actually when people are told to segment. So the same parts of the brain respond do the segmentation, whether you do passive segmentation or you do active segmentation, when you're told to do the segmentation. It's just when you're actually told to do it, it's much more pronounced.
What are those two plots there?
Sorry?
What are those two lines there?
Can you repeat the
In each of the graphs, what do the
So this is where an event boundary occurs.
yeah.
And this is the brain response at this area. This is
So those are
in the
total
posterior
activations.
cortex, yeah, and this is a bilateral response
Okay.
in the
Oh,
posterior
I see.
cortex. And there is interestingly enough, it's asymmetric response in the frontal cortex.
And so what's the green line and the red line?
Also, the green line and the red line is the
that's-
intensity of
thank you.
response in these areas. So what this is saying, well, here's an event boundary, and the activity actually started increasing. A little bit before it, but it definitely was higher after the event boundary. And so this is for large-scale events, and this is for really small, if you actually try to say, well, I'm looking at really very small scale event, very fine events. In both cases, there is always increase in brain activity in these areas. But again, so the interesting thing is, it's not that the increase starts exactly where the event boundary is. It's actually sometimes a little bit before it, sometimes a little bit after it. The strong response is, the most increment in response is always quite after the event boundary. And there are many reasons for this, but one of them is, to a large extent, these precise temporal event boundaries are fake. They are really a researcher's invention as opposed to the way our brain works. I mean, so there is, in perceptual organization, there is sort of this whole big issue that what's brain time as opposed to event time, right? It's quite different, right? In a way, if your brain did not use just the event time, you would have actually seen, we all see this, but you can see it even more. If I was actually further away, my speech would be not synchronized with my lip movement. But my brain is compensating for that. So there is this, that's where this uncertainty in event boundaries is, that first of all, these events, some of these high resolution events are so fine, somebody moving the lips, you may have actually missed it. Some people, when two of us communicate and you don't hear us, you may think we communicate as we're very close, but as I move away, you say, well, the connection is broken. But for different people, the distance that you actually have to move away is different. So this notion of precise event boundary is quite fake, but that's where we are. In order to evaluate algorithms, you have to match everybody else uses precise event boundaries, so that's what we have to use. So actually this is how do, and in fact you can ask what is the scale? It looks like the scale is, time scales. It's really not time scales, precisely because for our perception, time doesn't really make much sense, or at least we don't understand what sense it makes. So what really is the scale is what is the level of surprise. The reason why we perceive an event boundary is because we are surprised. What's in our working memory does not match the input signal. And we have to recover, we have to change the study of the working memory. That's what's an event boundary. And you can, the level of surprise is a different level of memory. Actually, this is a very interesting point why, so to me, I always love this part because, you have to give it to Adman. Once in the 60s, they were the smartest people alive. They've been using event processing, event segmentation to actually design good commercials. So it is actually well known since the 70s at least that there is improvement. So the quality of long-term memory is different around event boundaries. What you remember around event boundaries, you code better and better quality. So in fact, people have used this to design good educational movies. one way to actually make a point, if you actually have a good YouTube video, is, and if somebody's droning right now for half an hour, is just do a cut. People will remember the cut. People will remember not the fact that there is a cut, but they'll remember what happened around this cut. Just put a little commercial, make them blink. They'll remember the formula before that. So in fact, that's actually sort of that's been used a lot. One of my favorite videos is, there is a really expensive and very bad commercial with Paul Eric. Nobody remembers what was it all about. At the time, it was very expensive. It was $5 million for 20 seconds. Everybody remembers Paul Eric came out of something. What was it all about? Nobody remembers, because it was one continuous shot. She was just coming out. And they put the text for what they were selling in the middle of the commercial. If they had put it in the beginning when she was walking in, that's an event boundary, you would remember. If they put it at the end, you would have remembered it. Putting it in the middle was $5 million wasted. So the funny thing is, I was explaining this to my students, nobody knew what Derek was. So they feel very old. Well, they don't know what a gramophone is, they don't know what a turntable is. So. Well, they thought, oh yeah, I read about it in Wikipedia. Makes you feel ancient.
I have a question about the graph again. So you pointed out one of the points that you made is sometimes basically the activation patterns start rising even before the event, the kind of objective event boundary.
Right.
So I'm not familiar in this literature and I'm not expert no way in the event segmentation, but are there any possibilities that, regardless of the actual event boundary in the perceived event, brain is at the smallest level, that means the highest level of resolution, they are doing the sort of the very kind of almost some sort of interval-based, regular-based detection of segmentation. Then later on, at the more the lower level resolution, they do the more kind of flexible detection with the event boundary and superimpose and do some sort of computation to make an adjustment.
So attention kicks in, which takes time.
Because probabilistically, even when there is nothing, absolutely nothing is happening in the world, I think evolutionarily speaking, there got to be some sort of probabilistic segment of how often things changes, especially at this very, very small level.
Yeah.
Otherwise, how you can,
So I'll tell you where what videos were taken.
Okay.
So something was happening all the time. These videos were mostly a single person. So this is Jeffrey Sachs's. So it's actually a very stupid video. Somebody is sewing, and they were just watching somebody's hands as they're sewing. And still people can perceive an event. The needle moved in some crazy way. So something was happening all the time. None of it was tremendously exciting, unless you actually do bubbles for a moment. Now, the nice thing about it is they also done, so and again, this is very typical what happens in this literature. They actually, this is for these really not very interesting events. They've also done extensive studies with Hollywood style videos. So, and the results there are, again, similar curves. I didn't show you somebody else's work. There they can actually sort of identify even more interesting things. There are different parts of the brain which fire up precisely when somebody kisses, when there's a handshake, when there's motion. But anyway, the point is that what we want to exploit is, yes, we do. So it's an automatic process. What we want to do is an automatic process. And for me, I actually have to deal with automatic process just because it's a huge data set, and I have no time to have people train algorithms, and there is no reason to train them if the brain is doing it anyway. So nothing. And I have no time to tune parameters. It's just impossible to tune parameters. So again, so what's the problem? Now the problem is to look at these field grade videos, which are ad hoc videos. Somebody's taking picture of something they care about, and try to find out, try to segment them at some level at least, where, because we actually care about the measuring participation of level of participation of people, we basically try to look at who are the core people that are doing the main interaction that seems to be interesting to operate. And an event boundary, to us at least, and to the observers who actually can label our videos, was when this core group changed. They didn't react so much, as you can see with this case, they didn't react so much when the quality of the interaction changed. It was still these two people communicating, and most people say, well, that's the same event, no change. The fact that they kissed was caught by just very few people. So what you have to do is what actually apparently also our brain is doing. This event segmentation is is accompanied by a parallel process, which is we're continuously measuring who do we care about in the scene, who are the core individuals. So what we have to do is we have to have an algorithm that measures people's participation. Based on this, figure out who are the core people and who is the background. And then as these core people change, we'll put event boundaries. Again, because it's automatic, it's somehow based on some, it's going to be based on perceptual organization principles rather than tuning parameters or training something. So the principle that's the first principle, the zero principle, is that what I said before, scales are based not on time scale, it's really based on how much you're surprised. So in a group of 15, if one person moves out, is this important, is that important? So as I said, we have this parallel process, which is measuring people's participation, level of participation. Our first real principle is that we are already told that. We may not know it, but we are told that by the operator. The very fact that he's keeping somebody in frame, somewhere in the center of the frame, or hopefully he's trying to return back to him, is already telling him that he cares about this, he or she cares about this person. This person has high participation level. So there is sort of some funky math. So basically what we measure the level of participation by, so we look at all the actors we can recognize in the video and to each actor we assign a participation level. And then we can then say, okay, for the whole community, we can measure what's the total level of participation, how active is this video, which is measured by this formula. This is actually, so this is called the incidence index. So in some ways this is related to the fact, if I look twice at the scene, what is the chance I'll be looking exactly at the same group? So the next principle that we have is that actors can be brought, that of all the people in the video, because of the way these videos are taken, there is one group that the operator is caring about. This is the high participation, and then there's the background. So we want to find out an algorithm that actually breaks, in each frame, breaks all the individuals present into foreground, core participants, and background participants. So most perceptual organization principles are pretty simple. They are based on, they sort of underline automatic processes. So here the principle is, the high participation individuals as a group have higher index of participation than anybody else in the group. Pretty obvious, but it's a principle. It's a phenomenological approach. You just look at data. I don't want to invent very big theories. I'm making some very small, simple assumptions and trying to build my models based on it. And the other thing is, at this level of segmentation, the core individuals, if once I decide what my core group is, among them they all count equally. So what that means is, if I think of the probability distribution of what's the probability that somebody is a core individual, if I look only at this group of individuals, it should be pretty uniform. So whatever this distribution is, for them it should be like, you know, all of them should have probability 1 over n if n is the number of core individuals. So based on this, we can now actually start in each frame. We look at all the people in the frame and we start throwing out people. So if you have some way, so what I should say, suppose we do have some way of measuring, and I'll show in a moment 2 different ways, some way of measuring the participation probability for an individual in a frame. And I'll tell you, so assume that we can measure the participation of an individual, and I'll show you at least 2 different ways to measure that. Then once we have a way to measure the participation of an individual, we start with a full group and we start throwing out people with low participation level. And we keep getting this nested. So now we throw a few people out and look at what's left. And then we have to make a decision. Is this really the core group or not? How do we make the decision? I mean, one way to make the decision is to look at this group that's left and say, well, if this was the core group, they should all, at this, when I recompute their participation, they should all participate about equal. So I keep doing this, I keep throwing out people. So I throw a few people out, look, is this group good enough? If it is, I stop. If not, I keep throwing out, and whatever is left is my group alpha. This turns out to be a finite process, my group of core individuals. So once I can actually break, in each frame I can decide who the core people are and who the background people are. Now I can actually start looking at the sequence of frames and try to define a scene. It's not a scene, yeah.
Just a clarification, you are doing this only on the frames level. You are not segmenting out individuals and doing, okay.
No, just in the frame level.
Okay.
Now, the nice thing is, so now I actually have to look at all these different frames and say, well, I have to start putting boundaries on this frame. So a subscene is basically a continuous sequence, well, it's a contiguous sequence of frames in which one set of individuals remains core, and when this set of individuals changes, I have another scene. So this is how the process goes. Based on this, you can actually now define an algorithm. It's sort of a French-legal algorithm, but it's sort of a tree. So you start over all frames first, and you can figure out, look at each frame, and then over all frames, who is the highest, who are sort of the highest participation people. And that's what the first algorithm says. Well, there are only 3 people. This is sort of a very stupid video, but otherwise these graphs become very large. Once you do this, it basically says, okay, over the whole set of videos, person 2, this guy with a hat, seems to have the highest participation in all the frames. And the other 2 people are sort of background. And then I can actually break off and I say, okay, now let's see if I can make this part, if I can find subscenes, if I find contiguous frames where he really is a core individual. And then I'll look at the rest of the frames. So basically, if you look at the leaves of this graph, these are your subscenes. So basically this says there is a subscene from frame 0 to frame 30 in which person 1 was the core and nobody else was present. He was alone. There is another sequence of frames between 31 and 38 where nobody was present. So that was an easy one. But that's actually sort of important. Then I obviously missed it's 31 to 38. Where is 39? From 39 to 116, there is another subscene where this principal guy was the core individual and nobody else was present. And it goes on and on like this. what really happened, this video actually turns out it's in a bar. Somebody was taking a shot, sort of a video of a conversation. And because these guys were actually spread out in the bar, he actually followed unknowingly Hollywood video grammar because he was taking 180 shots. He was looking at the first person that was actually talking, and if you turn out to the next person who was talking, this is exactly how you actually do a well-composed video. Just break it into shots. Then he was looking at the next person, and it's also doing the sequence of 180 shots. So that's what algorithm is. So what this tells me is actually gives me two pieces of information. It gives me a summary of the whole video. Who is at the very top? Who is who are the highest participating people? And then it gives me sort of the different events. As I said, the events could be not what you call events, really, because you're always thinking at very high level, or at very low resolution. You're thinking about something really meaningful, me slapping you or me stopping to talk. It's much more subtle than that. But this was all assuming that you knew how to measure the participation of an individual. And how do you do this? Well, the easiest thing to do is to say, well, if a person is present in a frame, he's important, right? And it's sort of just being present. And again, there is an obvious counterexample that's not a good measure. And a counterexample, there's this movie Being There with Peter Sellers, who was just the guy that was standing next to the prime minister. He was completely doofus, but he was always there. Again, the reason why this is actually important is a simple way of measuring participation. And unfortunately, whatever algorithms we design have to work with our current person detection, recognition, and tracking algorithms. Our current person detection, recognition, and tracking algorithms suck. They are horrible. We really cannot recognize people very well unless we tune. What we can say is if a person is present, but we can't really get in a cluttered video, we can't really extract a face mask unless we tune. So we actually had to write a whole paper about this that basically tags people. So it just says, if you're present in this frame, if you're present in that frame. The way this works is actually you never track the full person. You sort of dynamically find some feature that's really prominent about a person, and you try to track that. And the idea is to find as small a feature as possible and as central to the individual as possible. So you actually, the reason why you want it small and central is because then the probability of being included in the next few frames is very low. So if you do this tagging, we actually have rates of, and they're not great. I mean, our rates of accuracy rates are about 78%. They're not great, but if you actually look at real detection and tracking algorithms, their rates are about 40% in multi-person video, at most 44. The best algorithms are actually, forget about tracking a person, just look at each frame and recognize everybody you can recognize. So it's tracking through recognition. And that requires a lot of training. And even then, the rates are about at most 60%. It's because you're trying to pull too much information. There is some theory that most of the times when we actually sort of analyze the situation around us, once I know you're here, I don't really have to recognize your face all the time. When you actually go away, I'll notice, but that's about it. So this is one way to measure. Another way to measure, which is much more clever, is to say, well, this person, the operator really cared about. If I can actually extract a face mask, I can also sort of measure the probability. How central is this face in the frame? What quality of shot was taken? Was he trying to take a full shot of the face? So I can actually measure the size of the face in the frame and the centrality. Now, if I had automatic algorithms that can do this reliably, I have a pretty good measurement of participation that I can then use to do event segmentation. The unfortunate thing is the state of the art is nowhere near. The data we have using these measurements are basically, I had a bunch of graduate students who paid very well to grow square boxes in the frame. So, So at least with these two measures, you can actually start looking at the video. So let's see. So we had 6 videos, different sizes, a number of frames. You know, think about it, it's 30 to 30 frames per second. So this is about a minute worth of video. This is about 8.5 seconds. These are very short videos, precisely because people are sort of running around. They're shooting as well as they can, and they stop. So when we ask people to mark events, in this long video they mark 6 events. So here 13, 20, 19, 6, and 4. Again, most probably when you ask a person to mark an event, he's actually marked, unless you really tell them, think small, think really, really small. They will mark on the low level resolution. It's actually going to be an attentive process. So what we want to do is, well, first, if you actually try to use standard video segmentation algorithms which rely on finding video shots, you're dead on arrival because they're mostly no video shots. So if your events, if your scenes were composed by standard video shots, you should have, you know, each event is a few video shots, so you have to have more video shots than number of events, right? And that obviously doesn't work. Here you don't have enough video shots. Here you do have, I have no idea how this happened. Oh, that's actually, let me see. Yeah, that's actually a news video where the camera is really zooming in and out on a person. Here you don't have enough video shots. There's only one video shot, but there are plenty of events. So what we actually wanted, we actually looked at our algorithm, and so we actually detected 19 of these subscenes. So you have enough to patch together the number of events. And that's actually the stupid participation measure, which is just being present. The reason why it works there is, again, because these are videos taken by somebody who cared about what they were doing. They wouldn't shoot something accidental. So the next thing in the evaluation that you have to do is, what I was showing here, is to see that so this is the crazy thing. So we have actually detected tons of shots. The reason is a lot of things are happening. But for each high-level event segmentation, I can group all of my low-resolution shots and get one of these high-level resolution shots. And that's your measure of success. You could argue, well, then you can do very easy. You will always succeed. Just over-segment. Put an event boundary in each frame and you're in business. Well, there are other ways to discover it. That's not correct. The other thing, though, to measure is that, of course, here it looks like there is alignment. It's always never perfect alignment for the simple reason that people don't agree where the boundaries are. That's where we are. So we actually have this. This looks like a high resolution. So we've found a way to segment videos. It's purely semantically. It's the meaning of the interaction between people. It is a higher resolution, so you can actually patch together from lower level events. And the next story is, well, how do you use these? In a sense, these are atomic units. How do you use these atomic units to actually patch the different levels of events? But at that point, this gives me actually a summary of each video. Actually, I have the people who participate in it. What are their level of participation of importance, and what different actions do they participate. The other reason why this is important is that when we do video segmentation, a lot of the algorithms, they're black boxes. You basically take a bunch of training videos for activities, and you train on them, and then you do recognition, then you do segmentation. So how do you decide what are the important, what you should be training on? Well, the typical examples are fights. So there's fights, people falling because of somebody. There was a famous accident. A lady was in the hospital. She was on surveillance cameras. People were looking at her. She sat and then fell off the chair and died. Nobody took care of her for hours. Suddenly that became a very important topic. People leaving suitcases on the ground for all these reasons. So these are high-level events that somebody has decided, some analyst has decided are important, and that's what we train on. But life is full of many other events, and it's actually important to find what these other events are so we can train on them. So that's where we are. And as I said, this is sort of a small part of a very large 7-year-old project. So, they just allowed us to publish this, so this was actually published at this international conference in pattern recognition.
So let's thank the speaker and let's open it up for questions.
Go ahead.
I was watching the CNN news where they're trying to decide or identify the guy that may have beheaded
Yeah. There is also acoustics there.
acoustics. So
Yes.
you get involved with acoustics too?
I'm not an expert in acoustics. I have people in my group. But a lot of these videos, the sound is pretty lousy. You have to actually filter it because again, you have wind.
Oh.
So here, these are stage videos there, so you can actually hear the speech. That's why actually what acoustic is being they talk. They told somebody else, they told some different guy that some. Rapper or his job here and come around and listen to him because he's identified the voice. A very related video to this, I'll come back to this. So the Boston bombing.
Yeah.
That's a very interesting video, but there we had an extra cue. We knew when it happened, the location, so we could just go back and last 1 hour of videos, and that's it. And there you're not allowed to use automatic algorithms because this is law enforcement. So, yeah.
Say you might be looking for something using, this system. Is there a way to plan for, like every mission possible movie you ever see, it's the misdirection. You see the fight, but you don't see the guy leading the briefcase. Your attention, you're misdirected to the fight event. And nobody notices it, but on a surveillance thing, you go over and over and over, and finally some person goes, "Oh, look at that."
So that was actually.
Can you find that?
So the interesting thing with surveillance is that. So the reason why one of our sponsors is actually funding this is a lot of these surveillance videos are actually not kept. And the government agencies are very upset, but they can't keep them. So basically, they look at it, they find an event, they take a few frames of it, they think are evidence for the event, and they probably take out. It's just too much work. So now they're using the system to actually parse the videos and see if they can extract some things. So if they can actually find things that we missed.
Yeah, but nobody would be pushing that.
So again, there on a surveillance video is a bit harder because on a surveillance video, so the way it works is on a surveillance video is like stream of consciousness. It's like it's this big drinking from fire hydrant, everything flows through. So the way it works really is you can go through some of these sub-events, sub-scenes that we discovered, and actually try to match them to different parts of the surveillance video. Now the issue is how do you match the sub-scenes with other. It's a whole new conversation. The way it used to be matched is usually people will choose if it's automatic. If it's manual, then just look at the whole video. But if it's automatic, they would actually choose the most informative frame. Basically keyframe, because there's this idea about implied motion that people recognize a motion just you don't have to look to the whole motion, recognize it just from a snapshot. Usually it's sort of the most exaggerated part. The trick with this is it actually works great when you have macro motions, like Usually it's used for people fighting, which are big motions, or people jumping, or people running. It doesn't work when people are talking. When you do these small emotions that are involved in day-to-day interaction, implied motion doesn't work. Unless it's a very strong reaction. So yeah, in facial expressions, implied motion also sometimes works. You know, people say, you know, you can recognize a smile by just one frame. Actually, I'm not sure. Sometimes I think he's trying to. But for these small everyday reactions, you actually need a couple of frames, sequence of frames. So there's snippets, and then how do you match these snippets is actually how do you encode them so they're actually matchable. It's another project that I have. That's on another ranges. But this whole issue now is small, you know, holding your hands all about.
John?
Yeah, it seems like I like your definition of an event being something like a surprise. You know, people recognize a surprise, and I think for like lots of surveillance situations, it would be a matter of like training, you know, essentially computer learning, in which the computer has to learn what a surprise
What is a surprise?
We recognize it because of our experiences. Somebody reaching in his coat. And it's kind of, it's not a usual event, you know, either he's reaching for a wallet or she's reaching for a gun, you know,
So on a brain level, and again, I'm another cognitive psychologist, I just, you know, talk to a lot of them and sort of, they convince me about things I read, it's like religion, I get it completely wrong. That's what I believe in. The surprise is when the intensity and changes in your working memory. When you have a lot of changes in the working memory, chunks in the working memory, that's actually an indication of surprise.
but for, let's say, a surveillance camera, you know, what you'd be training the computer to do is look at, you know, events throughout time. So, for instance, if you're down at the port watching, you know, containers moving around, and container movement stops at 3 in the morning, the computer would recognize, okay, all of a sudden there's 3 in the morning activity. That's a surprise.
Yeah, that's sort of, yeah, the big thing was always abnormal,
pattern
recognition. So that's what our brain seems to be doing all the time. It's finding abnormalities all the time. That's what we're looking at.
looking at patterns and figuring out what doesn't fit the pattern.
It's basically when he tries to do some work. That's when he gets upset.
So far you're only finding events and not
The sub-events, the small sub-events.
You're not putting any meaning associated
No,
with those events.
that's the analyst part. So, and again, that's a whole different story. When you give this to analysts, actually getting agreement between them is a very interesting observation. So we actually had to create a whole new way of measuring agreement. Because most agreements in segmentations are exactly based on how these temporal boundaries are aligned. But they're meaningless. What really matters is what's the quality. How much do they agree on what the quality of their boundaries? That's where that's another big that's for analysts. Because we don't know. I really don't know what's normal, what's important to them.
So kind of a follow-up on that question, because that's my definition of semantics, is the understanding of the scene. But you have grammars now that describe more of the structure of the video. Did you look at it and compare and contrast different grammars, or try to clump them into groups?
So we have some, we're working with stochastic grammars, but the truth of the matter is the choice of the grammar is the choice of the analyst. The grammar is appropriate for the language he speaks, he writes. Different analysts will apply different grammars, because for some people, some things are events, for other people, they're not events.
I thought the grammar was the function of the video scene that was being analyzed, rather than...
No, in a way I'm extracting, if you think about it, I'm extracting verbs and nouns at best. I'm not matching them together in sentences.
Okay.
There is a whole part of this, is what you're seeing here is the action. A whole very important part is to actually try to recognize what's happening in the background, what are the scenes. the physical things like this is happening. Unfortunately, in videos like this, you can't tell because people do care about the people they're shooting. So most of the frame is actually taken by teams. You see very little of the background. And that's sort of another big problem that we actually have, because we also have to tell people where is this.
So in human cognition, I think as far as I know, I think the most of the thing is not completely data driven. It's the expectation driven as well, and
Yes.
it interacts. So according to your kind of the one of the challenges, sometimes the small, even though the small segment is not automatically defined in that moment, but it's going to be actually the influence from the higher, the function of how the bigger chunk of the event is determined is going to also determine the lower level.
So yeah, so what I'm describing really is a bottom up.
That's right.
It's a bottom up based on very simple perceptual reflection.
Yeah.
And it doesn't require any awareness. There's no attention that actually is kicking in. There is actually a lot of attention in this algorithm that we're using to tag people, because what it does is it sort of finds a marker and follows that, and then the person exits, or the person gets moved, and then it has to go back and look in the next frames and see if this person came back. That's a very attentive algorithm. It's extremely heavy computation because you have to do recognition and you have to explain what really happened. So there is a tension in the way this top down comes in actually the way you compute it.
Yeah, I think what's interesting is from the psychological reality of the segmentation. So there are two issues. One, you actually segment online basis moment by moment, and then the way in which you are going to be subsequently remember it. So the way the literature suggests the way you remember even the smallest segment is partly the function of how you define the entire situations. So obviously, it's bi-directional things going on.
When you say remember, so the issue is most of this stuff doesn't go in long-term memory. It just stays in working memory.
Or it may be going there, but it may not be organized in such a way to be retrievable in that way.
Right. So the thing that's going to be going is really around the Venn boundaries.
Yeah. So the boundaries there.
So, and you say you've got, whatever, 7 terabytes of data.
Yeah,
Is that all classified data, or
well, we have
how you
as I
manage
said,
to publish?
so we have a civilian version of the data.
Okay, so that's what you publish with.
Yeah.
And then you just do screenshots of the video, or do you put
No,
up
so
supplementary
the civilian
information?
version is because we now have pretty good description of what the videos are. We know what the gist of the videos are. We know what the types of events are, and then we can look at commercial videos and find, or YouTube videos and find videos that have similar composition. So these videos are actually, I have to put them on a web server so people can test it out. So we cannot publish the 7 terabytes of data, but we have about 4 terabytes of data that are civilian are very similar. And again, there is also an issue because, you cannot publish if the project can be backtracked from the data, we cannot publish. But if the real task of the project is backtracked from the data, we cannot publish. So we can do it. But it's a pretty natural task. We all have videos that we have taken, and we all want to know why did we took it when somebody else took it. So that's not possible. But yeah, but we are constantly looking for